This is the town of Almaden in Spain. From this hillside, it isn't easy to see what's so special about it. But here, for hundreds of years, they've made something that's had a hand in many great scientific discoveries. It's a chemical substance with quite extraordinary properties. What they make at Almaden is mercury. Liquid, metallic, and beautiful. From the mine at the bottom of that shaft, there comes a red-coloured mineral called cinnabar. When the Romans mined here 2,000 years ago, it was treated like gold and carried to Rome under armed guard. Ground-up cinnabar is called vermilion, and vermilion was one of the most pricey pigments in the classical artist's palette. When Rubens painted his remarkable Three Graces, he used vermilion for the delicate red colour of the roses. Vermilion was also an expensive cosmetic, so its use for the blush on the women's cheeks was doubly appropriate. But today, we're not interested in cinnabar because you can make vermilion from it. I've come to the Cuevas mine, which is about 10 kilometres from Almaden. This rock is what comes out of the mine. Some of the cinnabar in it is covered by silvery globules. You can see some down here. And in fact, they're all over this rock. That's mercury, and I get a lot more of it if I just heated the cinnabar up. This programme is the tale of 4 great debts that science owes to mercury. But before we start it, let's learn a little more about mercury itself. Despite the number of empty flasks waiting to be filled, total mercury production is small compared with that of metals like tin and lead. So it makes sense to fill the flasks manually, even at Almaden, the world's largest producer. The standard helping of mercury is called a quintal and weighs 34.5 kilograms. That's getting on for twice your baggage allowance in a modern aircraft, and it all comes in one small chunk. Each pallet load carries 52 flasks lashed together and weighs nearly 2 tons. When the lorry reaches its maximum permitted load, its container still looks almost empty. Today, the load turns east for the distribution centre of Valencia on the Mediterranean. But once it went west to Seville and the Atlantic. In the 16th, 17th and 18th centuries, Spanish galleons carried Almaden mercury across the ocean to the Isthmus of Panama. From there, it passed to Mexico and Peru, where it was used to extract unprecedented amounts of silver. This silver played an indispensable part in the creation of the first maritime system of world trade. Mercury reacts with a precious metal like gold and forms an alloy called an amalgam. Given enough mercury and enough time, the gold will dissolve completely to form a liquid amalgam. The same thing happens with silver. When a few drops of mercury are dropped into a solution of a silver salt, the mercury swells up into a solid tree-like structure. This was once called the Tree of Diana. It's solid silver amalgam. But if you start with more mercury, the amalgam is a liquid. When it's heated, the mercury boils away and leaves the silver behind. Mercury can be used to extract gold and silver from its ores. From about 1550 onwards, Spanish-American silver was produced in this way. Much of it was turned into coins, like the famous reals or pieces of 8. It then flowed back into Europe, where it fueled a new world trading system. Here's a story to emphasize the value of mercury. In 1756, there was an underground fire in the Almaden mine, and mining became impossible. The miners were put to work, building a defensive wall around the village of Almaden Echos, where the mercury was stored. 2.5 years later, they finished the job, and the fire was out. Mercury production started again, but this time behind a high defensive barrier that prevented pilfering. We're now in the centre of Almaden, and this memorial is a tribute to its miners. It's a mark of respect for the contribution that they've made to the prosperity of not just Almaden, but Spain itself. And it's a good place to set the scene. This glass tube is about 1 metre long, and it's sealed at one end. I'll dip it into the water and tilt it. The air bubbles out, and water slowly fills the tube. Right. Now I'll lift it, keeping my finger over the open end, which is underwater. Now I'm going to take my finger away. What will happen? Well, I've just done it, and there's absolutely no change. The tube stays full, and no water runs back into the pool. There's something called atmospheric pressure, which presses down on the surface all around the tube and is transmitted through the water in all directions. It can even go around the corner at the bottom of the tube and prop up the water column inside. So the pressure of the atmosphere can prop up at least 1 metre of water. But what would happen if this pool contained not water, but mercury? So the pressure of the atmosphere can prop up at least 1 metre of water. How much mercury can it support? I've got enough mercury here to answer that question. About 12 tonnes to be precise, and of all of it under strong ventilation. So let's do the experiment again. The tube goes in, and mercury slowly fills it. Now I'll lift the tube vertically, but keeping my finger over one end. So far, no difference from water. The tube is full. But now I'll take my finger away. The mercury falls, but it only falls so far. When it stops, there's still a column of mercury standing above the liquid in the surrounding pool. This experiment was first carried out by Evangelista Torricelli in Florence in 1644, and it caused a sensation. What was holding the column of mercury up? Torricelli's now familiar answer was simple and direct. We live submerged in an ocean of air, and the air is heavy. At sea level, the air presses down just hard enough to support about 76 centimetres of mercury. Torricelli's experiment was soon repeated all over Europe. At sea level, the air presses down hard enough to support 76 centimetres of mercury. But if Torricelli's right, then on mountain tops where there's less air above us, the air will press down less hard, and the height of the mercury column should be less. In France, Blaise Pascal persuaded his brother-in-law to do Torricelli's experiment in a monastery garden in Clermont, and then to carry it up a nearby mountain and repeat it. The height of the mercury column fell by 8 centimetres. It all fits. This beautiful piece of science was possible because the Torricelli experiment is portable. And it's portable because the mercury column is short. Why is it short? Because mercury is a very dense liquid, a liquid so dense that cannonballs float in it. Torricella's experiment changed our view of the world. It gave rise to the science of meteorology, because here was the first barometer. It was soon noticed that the mercury column was usually shorter in stormy weather. In storms like the Great Pacific Typhoons, sea level pressures can fall to only 65 centimeters of mercury, and winds reach nearly 200 miles an hour. The atmosphere is a huge heat engine, shifting vast amounts of energy from one place to another. Torricelli pointed the way to this vision by giving the atmosphere mass and weight.
Today, mercury production is a sophisticated business. It was much less so in Torricelli's time. For over 200 years, up until 1928, almaden mercury was made in this little industrial plant. How was it done?
At this end, there are two furnaces. Each one was covered by a hatch. Inside was a grid. Cinnabar ore was piled onto the grid and heated from underneath by wood or coal.
The hot cinnabar then reacted with the surrounding air, and that reaction produced mercury. Now, the temperature inside the furnace was so high that the mercury boiled, formed a gas, and then passed down into these corrugated pipes. Well, each pipe consists of a chain of interconnected pottery vases. The bulbs are there to trap out grit and dust. On the underside of each bulb, there's a small hole. Now, when the mercury from the hot furnace entered the cooler pipes, it began to condense. And that condensation was encouraged by workers who patrolled this whole area, splashing cold water over the pipes. Liquid mercury then trickled out of the holes and ran downhill into the central sloping channel. From there, it flowed into a chamber behind this door. What happened here was chemistry, a science whose foundations began to take shape about 200 years ago. And mercury had a lot to do with the shaping process. Let's look at the reaction that took place in this plant, the reaction between cinnabar and air.
Things burn in air because it contains a particularly aggressive component. That component is oxygen. Now, cinnabar contains mercury and sulfur. When it's heated in air, the sulfur burns in the oxygen and is carried away as a gas, sulfur dioxide. Sulfur dioxide is acidic. It turns blue litmus red. This picture of burning as a reaction with oxygen became possible when pure oxygen was made from air. And it was mercury, which here you see left behind in the crucible, that did it. In the 1770s, Joseph Priestley and Antoine Lavoisier used mercury as a chemical vacuum cleaner. When mercury is heated in contact with air, it slowly sucks out the oxygen. As this happens, a red powder appears. This is mercury oxide, and it can be collected by scraping it off the mercury's surface. When this mercury oxide is heated very strongly, it yields up the mercury from which it has been formed. You also get the oxygen back, but with a difference. Now it's pure and free of the other gases in the air. So things burn more easily in it. These little experiments mark the beginnings of modern chemistry. First, they gave us a theory of combustion. Torricelli's ocean is a mixture. When things burn, they react with just part of it, the part that's oxygen, about 20%. Lavoisier's experiments also led to something even more fundamental. They showed that mercury oxide could be taken apart into mercury and oxygen, and then put back together again at a lower temperature. So mercury oxide is called a compound of mercury and oxygen. And that's why mercury oxide has the name that it does. But mercury and oxygen are called chemical elements because they can't be taken apart in the same way. They're basic building blocks. Modern chemistry began when Lavoisier built this distinction between elements and compounds into the working language that chemists use. Lavoisier also showed that the respiration of animals and birds was the slow combustion of carbon compounds in oxygen, though to do so he used a guinea pig rather than a stork. Nesting storks and cinnabar are conspicuous sights in these parts, but the storks are seasonal. The cinnabar is not. All over the Almaden area you find cinnabar-bearing rock. Some of it has been mined at the surface by open cast methods. That's what's happened here, at the Entradicho mine, where the terraces have been cut into the hillside. In Almaden itself, mining is underground and the miners are lowered down shafts. At the Cuevas mine, they can be just driven down in a spiral that follows the vertical cinnabar seam.
The Almaden mine has a small museum, and it's a good place to get our bearings. Mercury helped Torricelli and Pascal by being a very dense liquid. Priestley and Lavoisier exploited its unusual chemistry. There's a delicate balance between mercury oxide on the one hand and mercury and oxygen on the other. By adjusting the temperature, the balance can be shifted to either side. But let's not forget that mercury is also a metal. These are the wires of an electric bell. I touch them together, there's electrical conduction, and the bell rings. Now I'm going to dip them into mercury. Again, there's conduction. Mercury is a metal. Our next contributor is someone who exploited the fact that mercury is both a liquid and a conductor. He's the man on the £20 note. Michael Faraday did most of his research here in London at the Royal Institution, and in the basement they have a small museum in honour of his great discoveries. The work for which he's most remembered started with the discovery made in Denmark by Hans Christian Ørsted. When a magnetic needle is brought up to a current-carrying wire, the needle is deflected. In 1821, Faraday made a very careful study of the forces acting between a magnet and a wire, a current-carrying wire, and he summarised his results in a very simple way. The forces tended to make the wire rotate around either pole of the magnet. So, when Faraday brought one pole of a strong magnet directly up to the wire moved as it tried to start a rotation. Now this movement is a possible source of power, but here it can't continue because the wire is pegged at either end by connections which supply the current. What's needed is a different sort of connection, one that still supplies the current but allows free movement. Faraday made one from mercury.
The horizontal rod is one terminal of the electric circuit, and the top end of the wire is looped over it. The cork, where the wire dips into the mercury, just provides extra buoyancy. At the centre of the cup is one pole of a cylindrical magnet. An electrified wire passes over the rim of the cup at the lower right. As promised, the wire rotates around the pole of the magnet. This is the very first electric motor. It was years before technology took advantage of this discovery. Today, we're surrounded by electric motors. Skyscrapers, for instance, would not be possible without the invention of the lift, and lifts are powered by electric motors. If the motors stop, modern life stops with them.
There's an interesting connection between Faraday and mining. When Faraday first came to the Royal Institution, he helped Sir Humphrey Davy design a miner's safety lamp. A lamp whose flame burnt quietly even amid the explosive gases that coal miners so feared. In cinnabar mines, the threat comes not from explosions, but from poisonous mercury vapour. Seen in visible light, the space over liquid mercury looks innocent enough. In ultraviolet light, things look very different.
The mercury atoms above the liquid absorb ultraviolet radiation, so you can see the vapour billowing off the surface like smoke. Mercury vapour is the invisible enemy of the cinnabar miner. Prolonged exposure must be avoided. In Almaden today, the shafts are well ventilated, the miners only spend 8 days a month underground, and mercury levels in their blood and urine are constantly checked. It was not always so. 400 years ago, the notorious mines of Huancavelica in Peru were worked by native labour. Fires were often lit at the workface to crack the rock. Mercury vapour concentrations must have reached terrifying levels, and the life expectancy of a miner seems to have been reckoned in months. The volatility of mercury that threatens the miners is a sign that the boiling temperature of liquid mercury is not too high. That fact led to the last of our 4 discoveries. At atmospheric pressure, liquid mercury boils at 357 degrees Celsius, so it can be purified by repeated distillation. Here, the distillation is being done at atmospheric pressure. You get cleaner results in a near vacuum, where the mercury boils at about 70 degrees Celsius. Triply distilled Almaden mercury is 99.9995% pure.
So if you want a very pure metal, mercury is the obvious choice. That choice led a Dutch physicist called Kamerlingh Onnes to a Nobel Prize. To see why, let's leave mercury for a moment and turn to gold. To this gold ring, for example, or what's left of it. Gold is a very good electrical conductor, or, putting it another way, gold has a very small resistivity. And when metals like gold are cooled, their resistivity gets even smaller. But just how small can it get? In 1908, Kamerlingh Onnes got the chance to find out when he liquefied helium gas. By using liquid helium as a coolant, he was able to measure resistivities at minus 271 degrees Celsius, just 2 degrees above the absolute zero, 2 Kelvin. This figure from his Nobel Prize lecture shows what he found. Resistivity is plotted up here, the temperature in Kelvin along here. The curves are for different metals. Here's one for gold. Below 10 Kelvin, the resistivity of gold bottomed out at just 1/100th of its room temperature value. But it could be pushed even lower. This gold was 99.985% pure. Purer gold had an even smaller resistivity. Was it possible that the resistivity of very pure gold might disappear altogether? Now here, there was a problem. Onnes put it this way: even the purest gold from any mint in the world was not pure enough for the experiment. What's more, gold is one of the very best conductors, so changes in the resistivity of gold at low temperatures are very hard to measure because that resistivity is so very small. So Onnes looked for a metal of higher resistivity that could be made very pure. The obvious choice was mercury. Here's what happened when Onnes chilled mercury with liquid helium. The resistivity fell, and just 1.5 degrees above the absolute zero, it was less than 1/1000th of its room temperature value. But the fall wasn't gradual. Most of it happened at 4.2 Kelvin. Here, quite suddenly, the resistivity of mercury completely disappeared. Below 4.2 Kelvin, the mercury entered a new and very strange state. Onnes called it the state of superconductivity.
Liquid helium is needed to make mercury superconducting, but new materials discovered in the 1980s, like this black disk, become superconducting at temperatures easily reached with liquid nitrogen. Despite appearances, this isn't computer animation. It's the real world, the superconducting world. When a magnet is placed over a superconductor, it sets up electric currents in the superconductor's surface. Because of these currents, the magnet then senses the superconductor as a copy of itself. There's magnetic repulsion between the two copies, so the magnet undergoes levitation. Even with very large currents, coils of superconducting wire don't overheat, so they can be used to produce very powerful electromagnets. In magnetic resonance imaging, the human body is exposed to both the magnetic field of a superconducting coil and to a pulse of low-frequency radiation. The technique provides very clear images of soft tissue, veins, and arteries. Superconducting electromagnets are also built into a visionary form of transport which is still under development, the Japanese magnetically levitated train. The onboard magnets are cooled by liquid helium, and they repel more conventional magnets in the bottom of the U-shaped track. At high speeds, the train is lifted about 10 centimeters above the track. Magnetic forces between electromagnets in the walls of the track and the onboard magnets then speed the train on its way. The eventual target is speeds of over 500 kilometers an hour, 300 mph. There's a historical thread that connects this ambitious technology with Torricelli's little experiment. It's a thread of mercury, of quicksilver.
The creation of modern science has taken many hundreds of years, but mercury has always been ready to give it a helping hand. Torricelli and Pascal's work on the atmosphere was done in the 17th century, Lavoisier's chemistry in the 18th, Faraday's electric motor in the 19th, and superconductivity in the 20th. There isn't any point in speculating on the contributions that mercury might make in the future. But one thing does seem likely. So long as mercury is used, Almaden will produce it, because it's here that you find the richest mercury ores in the world.